another variation of the story. Each fork may be picked up and put down many times on each occasion that the philosopher sits down. Thus the behavior of the hands is modified to contain an iteration. Deadlock. When a mathematical model has been constructed, it reveals a serious danger. Suppose all the philosophers get hungry at about the same time. They all sit down, they all pick up their own forks, and they'll reach out for the other fork which isn't there. In this undignified situation, they will all inevitably starve. Although each actor is capable of further action, there is no action which any pair of them can agree to do next. However, our story does not end so badly. Once the danger was detected, there was suggested many ways to avoid it. For example, one of the philosophers could always pick up the wrong fork first, if only they could agree which one it should be. The purchase of a single additional fork was ruled out for similar reasons, whereas the purchase of 5 more forks was much too expensive. The solution finally adopted was the appointment of a footman, whose duty it was to assist each philosopher into and out of his chair. This alphabet is defined as follows. There is also proof of absence of deadlock. In the original college, the risk of deadlock was far from obvious. The claim that new college is free from deadlock should therefore be proved with some care. What we must prove can be stated formally as follows. There is also a problem called infinite overtaking. Apart from deadlock, there is another danger that faces a dining philosopher. It is being infinitely overtaken. Suppose that a seated philosopher has an extremely greedy left neighbor and a rather slow left arm. Before he can pick up his left fork, his left neighbor rushes in, sits down, rapidly picks up both forks and spends a long time eating. Eventually he puts down both forks and leaves his seat. But then the left neighbor instantly gets hungry again, rushes in, sits down and rapidly snatches both forks before his long-seated and long-suffering right neighbor gets around to picking up the fork they share. Since the cycle may be repeated indefinitely, a seated philosopher may never succeed in eating. The correct solution to this problem is probably to regard it as insoluble, because if any philosopher is as greedy as described above, then somebody, either he or his neighbors, will inevitably spend a long time hungry. There is no clever way of ensuring general satisfaction, and the only effective solution is to buy more forks and plenty of spaghetti. However, if it is important to guarantee that a seated philosopher will eventually eat, modify the behavior of the footman. Having helped a philosopher to his seat, he waits until that philosopher has picked up both forks before he allows either of his neighbors to sit down. Now I'll discuss about deterministic and non-deterministic approaches from the 3rd chapter. Deterministic approach. A process is called deterministic whenever there is more than one event possible. The choice between them is determined externally by the environment of the process. Example, the change-giving machine offers its customers the choice of taking his change as 3 small coins and 1 large, or 2 large coins and 1 small coin. Non-deterministic approach. A process is called non-deterministic whenever there is more than one event possible. The choice is internally made by the machine that runs the process. It arises from a deliberate decision to ignore the factor which influenced the selection. It is useful for maintaining a high level of abstraction and descriptions of the behavior of physical systems and machines. We exclude the events. The combination of change given by the machine may depend on the way in which the machine has been uploaded with large and small coins from the alphabet. Notation for non-determinism: P or Q to denote a process which behaves like P or like Q, where the selection between them is made arbitrarily without the knowledge of control of external environment. The alphabets of operands are assumed to be the same. Example: a change-giving machine which gives change in one of the two combinations